Hello guys, welcome back to Calculus. First, I just want to apologize about the inconsistency of the classes. I have mentioned that I'm traveling a lot in the past and I'm currently traveling a lot in the near future as well, due to some really chaotic things going on in my life. So this won't be structured the way class is typically structured for me. I won't have access to the same tools that I do on my normal workstation, so I've kind of just dubbed this Calculus on the go. I mean, I don't have my same workstation as before, but I'll still do my best to make lessons as consistent as possible and to keep them as similar to the original content as possible, as within my power to do so. So that hopefully won't have any real effect on the quality of our lessons. Hopefully we'll still get the same quality as we're typically used to. So let's talk about what we're going to be talking about in this video. Last few lessons, we have been introducing the concepts of improper integrals. We've talked a bit about convergence and divergence, and we had just a basic brief introduction of sequences and series as well as infinite series. So let's go over what the things we're going to be talking about in this particular video. So we're going to review improper integrals. It's been a while since our last lesson, so I think it's a really good idea for us to review how to evaluate improper integrals that can be evaluated. We also want to review the concept of convergence and divergence, maybe go over some definitions, and then some rules we can use to determine whether certain integrals converge and whether they diverge. And then after that, we have infinite series. So it's one of the big main ideas in this class. Like I said, the main ideas in calculus are typically thought to be limits, derivatives, integrals, and then in this particular class, infinite series would be the fourth big idea of a calculus class. So we want to make sure we have a lot of time to understand infinite series. And then the last thing we're going to talk about is applying our knowledge of convergence and divergence in infinite series. So infinite series, we'll find that they can converge, they can diverge, just like integrals can. And we'll find that they have their own specific rules to determine convergence and divergence. So there are certain rules we use to determine convergence and divergence of integrals. And then there are other really specific rules we use to determine convergence and divergence of infinite series. And we'll see that there is maybe just a little bit of overlap between the two. They have some methods in common, but other than that, they have some really specific methods to determine convergence and divergence in each case. So let's get right into it. We're going to start by reviewing improper integrals. So I thought it would be a really good idea just to ask ourselves, what is an improper integral anyway? We know what integrals are. We're pretty good with integrals by this point. So let's review just what an improper integral really is. And I apologize if my handwriting is terrible. Like I said, this is just kind of my on-the-go setup. I don't have the pen and the tablet like I'm used to having. So I apologize in advance for my bad drawing and my bad handwriting. So an improper integral is something that has an indeterminate limit of integration. So for example, suppose we're taking the integral of some function f of x, and we have limits of integration. We're taking the definite integral. We have some clear limits of integration. We have a start point and we have an end point. So let's talk about what an improper integral is. Let's just review that real quick. So an improper integral occurs when we have an indeterminate limit of integration or two indeterminate limits of integration. And what do I mean by indeterminate? Indeterminate in a calculus context refers to things that don't have a fixed value, things that can't be thought of as discrete values, things like infinity, things like 1 over 0, things like infinity over infinity or 0 over 0. Things like that that are technically undefined and don't have a fixed finite value. So this, well, I mean, depending on what f of x is, but in general, this right here is not an improper integral. This is just a normal integral. But if we were to take the integral maybe from 0 up to infinity, that's what makes it improper. This is an improper integral because we have the infinity as our upper limit of integration. So let's talk about determining if we can actually integrate something like this. There are going to be cases where we can integrate an improper integral, and then there are going to be cases where we can't integrate them at all. So we want to focus and review those topics. We want to focus on the tools we have at our disposal to help us determine whether we can actually integrate things like this, whether we can integrate improper integrals. So before we even do that, we have to review the concept of convergence and divergence, because they are so very important when determining if we can even integrate something like this, if we can even integrate an improper integral. So let's talk about convergence. Let's just have a brief review, a brief reminder of what convergence really is. So remind yourself that convergence in general, in a math context, not specifically with integrals, but just in a general math context, convergence occurs whenever it looks like we are approaching a certain value. So part of this part right here approaches a certain value. It sounds kind of familiar. You might remember that we talked about things like this when we were first studying limits at the very beginning of this class. When we first started learning what calculus really is, we started learning limits. This is a major part of limits, and limits are actually something we use as a really useful tool when we're determining convergence. So convergence occurs when a function approaches a particular value. Let's give us an example so we can have a really solid understanding of what this is in the context of a particular function. Let's see here. I like 1 over x plus 1, so let's use that as our example function. So we know what 1 over x looks like. It's the basic rational function. So the difference between this and what we have here is we're going to be scaling everything up by 1 unit. So instead of the horizontal asymptote being the x-axis, being y equals 0, the new horizontal asymptote is going to be actually y equals 1. So I'm going to use a blue line to show the new horizontal asymptote that we have. And then let's sketch the function. That's one part. This is the other part. So let's determine if this really approaches a certain value. So what happens if we take larger and larger and larger values of x? So we know that if we compare this point with this point, and we compare this point with the next one, and then the next one, we're picking bigger and bigger values of x. So we want to ask ourselves, as x gets larger and larger and larger, what happens to y? Specifically, does it look like y approaches a certain value as x gets bigger and bigger? And it looks like it definitely does. As x gets larger and larger and larger, we can clearly see that our curve approaches this asymptote. It approaches the y equals 1 asymptote. So we can prove then that this definitely converges. It converges to y equals 1. But to give us a really rigorous definition of convergence, it would, here, let me write this first. The function is convergent if and only if the limit as x approaches infinity exists. The limit as x approaches infinity of f of x exists. So limit as x goes to infinity. If the limit exists, then the function definitely converges. And that only applies to the positive side. We can also do the same for the left side. If we start at 0 and we travel more and more to the left as we pick smaller and smaller and smaller values of x, we could give ourselves a two-sided convergence definition. We could say that the two-sided limit converges if not only if this condition A is true, but also if condition B is true. If we turn this into a two-sided limit, if we have this one traveling from the left to the right side, that's what the minus sign represents. And I'm sorry if that's really small. Here, I'll try to make the next one a little bit bigger. The other condition would be convergent if the limit of our other two-sided limit of f of x, if this limit exists as well. And I'll write it a little bit bigger. So this is going to be another two-sided limit, or sorry, this one is going to be a one-sided limit. They're both going to be one-sided. This one would be the limit as x approaches infinity from the positive side. The last one, x approaches infinity from the negative. this would actually be x approaches negative infinity from the positive side. So we're starting from the right and working our way down to the left. So if both of these exist, then the function is absolutely convergent, but you'll notice how we don't really care about b in this case. In this case, we only care about what occurs to the right of the y-axis. We don't care about what's on the left side. So in this case, we don't even really need to consider a two-sided limit. We only really care about what happens on the right side. So it's no longer a two-sided limit problem. It's only going to be just a simple limit. We just care about whether y converges to a certain value, whether y approaches a particular value as x gets bigger and bigger and bigger. So we don't even really need the minus sign, but I just can't erase it. It's way too small. I'd be screwing things up in the process if I try to erase that, so I'm not going to bother. I'm just going to leave it there, pretend like that negative sign doesn't exist there. It is just the limit as x approaches infinity of our function of f of x. And this one definitely does converge because we know that as x gets larger and larger, it approaches the asymptote. In this case, it approaches +1. It approaches y equals 1. So let's give a complete limit statement in order to definitively prove convergence of our function. The limit, because it approaches a value of 1, the limit as x approaches infinity of our function is 1. So because this is true, it definitely converges, 100% converges. So that means that if this is our function, it means we definitely can integrate it. We can only integrate if we have something that converges. We can only integrate convergent functions. And remember our other condition for integrals specifically. We can only integrate improper integrals if they converge to 0. So let's take a look at this function. It does not converge to 0. We get closer and closer to the blue line. We get closer and closer to y equals 1, which means that we're going to have all of this space here. I think I can do that a little bit better. We're going to have all of this space that's there basically forever, starting with x equals 0. X gets larger and larger and larger. And then y gets closer and closer to 1. This space is never going to be depleted. This space is never going to go below a height of 1. It has a height of 1 right there. It has a height of 1 right there. So this space right here is going to increase on and on and on forever. So because this does not converge to 0, we can't take the integral. We can only take the integral of things that converge to 0. This converges to 1, thus we can't integrate it. It does converge in general, though. It converges to 1. So for integrals, it has to converge to 0. But if we're only talking about simple convergence and we don't care about taking the integral, we just say that, yes, it does converge. We can't integrate it, but yes, it does. We cannot integrate it, but yes, it does converge. But what if we wanted to modify this in order to make it converge in an integral sense of the word? What if instead of making this 1 over x plus 1, what if we eliminate the +1 right there? So let's take a look at what effect that has on our function. Whoops. So what that does is it moves the horizontal asymptote back to its original position. Instead of the asymptote occurring at y equals 1, it will now occur at y equals 0. So let's quickly change our definition of this limit. This is no longer correct. It now equals 1. The limit as x approaches infinity of our function f of x, well, we know as if we pick larger and larger and larger values of x, we can see that y would get closer and closer and closer to 0. So that's how we know for sure that the limit as x approaches infinity of f of x, that equals 0. And because it equals 0, we are able to take this improper integral. But actually, I want to make a quick point real quick. We can't take the integral going from 0 to infinity of this function. We can only take the integral going from 1 or another number greater than 0 to infinity. And let's quickly talk about why that is. So let's take a look what happens if we try to integrate the function going from 0 up to infinity. So we have a limit handling the end behavior on this side, but then we also have infinite discontinuity right here, which means that this area is never going to end. So it would work if we have it only works if we have one of these situations. It only works if we have one-sided discontinuity. This has a two-sided discontinuity. We have discontinuity right here as x approaches 0, and we have discontinuity right here as x approaches infinity. And for that reason, it doesn't work. We can only integrate things with one-sided discontinuity. But that is easily remedied. Instead of integrating from 0 to infinity, let's integrate from 1 to infinity. And you might be thinking it doesn't make that much of a difference. Why are we even bothering doing that? Well, it's because now if we're integrating from 1 to infinity instead of 0 to infinity, we only have one-sided discontinuity to worry about. So we have continuity here. We have discontinuity right there, and it's perfectly valid to integrate something like this that converges to 0 if we have just one-sided discontinuity. So it works very, very well. This modification has proved highly useful to us in this case, and we are able to integrate this function on the interval 1 to infinity. So let's get started. Let's crack on, shall we? I want to start by just replacing f of x with the actual function value. We know that that's 1 over x dx. Or actually, to save space, let's make that dx over x. It's the exact same thing. Let me just put the line right there. Such a huge integral symbol for such a small function. So now let's go ahead and see if we can integrate this. We want to integrate 1 over x. So if it's been a while since you've done some integrals, you might be tempted to use the power rule. You might be tempted to write this, hey, well, this is x to the negative 1 power. We can't really do things like that because that would get us x to the 0 power if we apply our normal integration rules, and things just kind of break and fall apart at that point. So instead, we want to ask ourselves, well, is there a particular function that we take the derivative of to get 1 over x? And the answer is yes, absolutely. The derivative of natural log of x is 1 over x. So because the derivative of the natural log of x is 1 over x, that means the antiderivative, the integral of 1 over x, is natural log of x. And remember that it's the fundamental theorem of calculus that tells us that derivatives and integrals are opposites. Tells us that integrals and derivatives cancel each other out. So the derivative goes away, the integral goes away, and what we're left with is just the integral of 1 over x is the natural log of x. It works really, really nicely. But we have to fix this real quick to fit our rigorous definition of an improper integral. And what I mean by that is we're used to finding the antiderivative and plugging in our endpoints. The problem with that is we cannot plug in infinity as an endpoint. It's impossible to find, for example, if we have a function 2x plus 1, what is the function's value when x is infinity? Short answer, it has no value at all. It's undefined. You can't plug infinity into a function and get a number as your answer. So that's why instead of approaching it like this as we're used to, we have to approach it with a limit. Limit is the tool that we have to use in order to conceptualize taking the integral of a function from a fixed value to a concept like infinity. So actually we want to approach it like this. We're going to change it to the limit as Greek letter alpha. That's horrible looking. I'll retry that. Limit as alpha approaches whatever this is. So in this case, we can see that alpha would be approaching infinity. Alpha approaches infinity of the integral. Instead of 1 to infinity, we're going to replace this with 1 to alpha of our function of dx over x. So this has more mathematical validity than what comes before it. Like I said, that's just because we can't plug infinity into a function and get a value. We can plug alpha into a function and get a value, and then only when we do that will we be able to get a sense of what happens when we take alpha to be increasingly large. If we take larger and larger and larger values of alpha, it approach infinity. So let's go ahead and take the antiderivative. So for purposes of time and convenience, I'm going to do this all in one line. I'm not going to have multiple lines working out the same problem. I'm just going to replace things with new information as I go. So we know that the antiderivative of 1 over x is just natural log of x. So let's take the integral. The integral going from 1 to alpha of 1 over x is natural log of x. So we're going to take natural log of x and we're going to plug in these endpoints. We're going to plug in alpha and then subtract what we get when we plug 1 into that very same antiderivative. Here, let me use maybe a bigger text size here. So we have the function natural log of x. And we are evaluating that from our high endpoint, which is alpha, all the way down to our low endpoint, which is 1. So let's go ahead and plug in alpha. So according to the second part of the fundamental theorem of calculus, in order to execute something like this, in order to evaluate this, we're going to do the function at our top endpoint minus the function evaluated at the bottom endpoint. So this would be natural log of alpha minus natural log of 1. And the nice thing about having this on video is you can go back and review this as many times as you need. And the previous information is always there at a previous date in the video. So I don't feel too bad about erasing a bunch of stuff. So we're going to evaluate the natural log of our high endpoint, and then we're going to subtract the natural log of our low endpoint. And that's not something we do specifically for this problem. That's just the way the second part of the fundamental theorem of calculus works in general. That just tells us the intuitive way to calculate the definite integral of a function. It's just going to be the antiderivative evaluated at the high endpoint minus the antiderivative evaluated at the low endpoint. So natural log of alpha, we know alpha is approaching infinity. It's not so easy to conceptualize this. So let's focus on this part right now, the natural log of 1. What is the natural log of 1? Natural log of 1 is 0. And the reason why it's 0 is because anything to the 0 power is equal to 1. So natural log of 1 is just going to be 0. And now we can focus on this part. So what happens to this as x gets larger and larger and larger? We can see that natural log of x would also get larger and larger and larger. This doesn't really approach a certain value. So this one does not work very well. And we've covered this a bit in the past video. I think this is my second time doing this problem, but it bears repeating because it's such a really powerful example. It's really powerful because it illustrates so many different things that we want to learn in this class, in the things we want to review. It helps us review the concept of convergence, helps us review the conditions under which we can integrate an improper integral, and so on and so forth. So this one doesn't work because as alpha gets larger and larger and larger, natural log of x also gets larger and larger and larger. So this tends to infinity. And of course, infinity is not a finite value. We can't have something evaluating to infinity. So this one doesn't work. So this is also a point that we got to in the last calculus video that I made. We wanted to determine if there might have been an easier way to do that without even diving into the calculus part of this. Is there a way to tell right away if this converges without even integrating anything? And the answer is yes. Remember that we had something that I called the p-test we use when we're determining if we can actually integrate something. I mean, at first glance, it might look like it converges, but the p-test is a really good solution to verify 100% if it conclusively converges. So it works if we have something like this, 1 over x to the p power. And remember that if x is greater than 1, then this definitely converges. If it's less than or equal to 1, it diverges. So let's go ahead and write those in. Converges if p is greater than 1. Diverges if p is less than or equal to 1. So we could have just done this right away from the beginning. We can see that this definitely follows the same format as we have right here. So we have an invisible 1 as our exponent chilling on the bottom with our x. We can see that our exponent is 1. And if we go over here and take a look at these conditions, we can tell that if x is 1 or less than or equal to 1, it diverges. So this one definitely diverges, absolutely. So we didn't even really need to take an integral. We could have just done the p-test right away to see that it converges. And this is just one more tool we can add to our already pretty impressive arsenal of tools we use to determine convergence and divergence of integrals. So we can't actually integrate this. Just because it fails this p-test, we can tell that it diverges and we can't integrate something that diverges. It has to converge, and not only does it have to converge, it has to converge to 0 for us to be able to actually integrate it. So I thought we would do some practice problems. We need to determine if these things converge, and if they do converge, we'll go ahead and evaluate the improper integral. So I have some examples that come directly from the book I'm using to teach this class, It's Stewart Calculus, I think 3rd edition. Really a great book, a lot of really great examples. I'm a big fan of Stewart books. I'm a big fan of all the Stewart Calculus books, and that's what I'm using for this course. So the first one we have is the integral going from negative infinity up to positive infinity, a step up from what we've been doing so far. And then our function we have is x divided by 1 plus x squared. And I think I'll just type that out. So this one is tricky. The thing that makes it more tricky than usual is because we have a negative infinity and we have a positive infinity. So there are certain cases in which dual-sided discontinuity could possibly converge, and certain conditions in which it could diverge. So actually, I think it might be really helpful to us if we could graph the function and get a sense of what the end behavior is. So let me fire up Desmos real fast, and we'll take a look at the function. So here we go. I've graphed the function, and there's something kind of interesting about this one. It is symmetrical. Or I guess symmetric. Symmetrical isn't a word. It's symmetric about a certain line, about a certain axis. So we can see that whatever occurs to the right of the y-axis is equal to whatever occurs to the left. These areas are equal to each other. They're equal but opposite, since whatever occurs to the right is above the x-axis. Whatever occurs to the left is below the x-axis. But they are equal but opposite. And if we're trying to find only area, we'd have to take the absolute value. We would have to limit the domain like this. We would have 1 plus x squared. And that we would limit the domain so that we only have positive value. So this would only be on the interval where x is greater than 0. If I'm even doing this right, I could be completely wrong. Shoot. I think I need curly braces. Nope. There we go. I think that's right. And then we also want to limit the domain of our other part. So this would be x is less than 0. But then we want to multiply it by -1 so we can move it to the top of the x-axis. We want to move it above the x-axis. So we're going to put a -1 out front. There we go. So the difference between this and what we just had is we only have positive area. So remember the distinction between the definite integral and the area. The definite integral is used to find area, but the two are not exactly the same. A definite integral refers a definite integral. I can't talk today. I'm sorry. A definite integral can return negative values, but the area can never be negative. It just does not make sense to have a negative area. So we'd have to make things positive like this in order to find the area. But if we don't have to find the area, it's okay to leave it like this. So if we were to take the area of this in particular, it would be 0. And we know it's 0 because everything that occurs to the right of the y-axis is equal but opposite to whatever occurs to the left of the y-axis. So the area under the blue curve plus the area under the red curve, it would be 0 just because they're equal but opposite. It's like saying this minus this is 0. So that would make the whole integral equal to 0. That's not a very good example. So I want to maybe approach this not as an area problem, but just as a simple, maybe not an integral problem, but let's actually approach it as an area problem. Let's make this part positive and see if we can find this area under the curve going from -infinity up to +infinity. So I can see something that it's a good opportunity for us to use kind of a lesser known trick in calculus. Whenever we have symmetry like this, we can take the integral only by finding half of this and then doubling it. So we could find either the integral going from -infinity all the way up to +infinity, or what we could do is we could find only this part and then multiply it by 2. And you might be thinking, why do we want to do that? Well, it makes things a lot easier and it makes things much, much faster. So I'm definitely in favor of that. Instead of going from negative infinity to infinity, let's go from 0 all the way up to infinity, and then we'll just double that result, and we'll get the same thing that we expect to have. So going back to the whiteboard. There we go. So we want to rework this integral so that instead of going from negative infinity to infinity, we're going to go from 0 to infinity, and we're going to multiply the result by 2. Whoops. All right, it looks a lot easier already. So remember, we want to determine if this thing converges before we can even integrate it. And remember that the conditions for integral convergence are that the function that we're integrating has to converge to 0. And in order for us to even evaluate this improper integral, if it converges to anything but 0, we can't do it. So let's actually go back to the white. Let's go back to Desmos for a second. Sorry, I might have left maybe a bit prematurely. So we can see that as x gets larger and larger and larger, y gets smaller and smaller and smaller. But that's not what we're trying to figure out. The real question at hand is, does it converge to 0? We can only integrate if it converges to 0. If it converges to 1 or 2 or anything but 0, we can't integrate it. So let's take the limit as x approaches infinity of this particular function. So we're going to take larger and larger and larger values of x, and then we're going to identify what happens to y. We want to just recognize the end behavior that y exhibits when x approaches infinity. And sometimes we have to go pretty small in order to get a good sense of what happens when x approaches infinity. So we can see that y gets smaller and smaller and smaller yet as x approaches infinity. And it definitely approaches 0. I think at this point we can definitively conclude that y approaches 0. So not only does the limit exist, but the limit equals 0. It converges to 0. So that's how we know 100% that we can integrate this. We can only integrate something that converges to 0. And I'm happy to say that this thing definitely does converge to 0. So let's go ahead and take the antiderivative and find our answer. So this one looks like a u substitution problem only because we have a second power of x on the bottom and a single power of x on top. Pretty clear indication that we want u to be whatever we have on the bottom, 1 plus x squared. And if we take the derivative of that, we get the following. We get du is equal to 0 plus 2x times the differential. And if we look at the integral, I can see the x. I can see the dx. But what I don't see is this 2. So we have to make some kind of a modification to take care of that, to take that into account. So let's take this differential equation. Let's take the du equals 2x times dx and divide both sides of the equation by 2. So divide this whole thing by 2 and then divide the du differential by 2 as well. This 2 is going to go away. It's going to cancel with this one. So we have 1/2 du is equal to x dx. And let's review our basic integration rules. Let's review what we have to do whenever we make a differential equation modifier like this. Let's see how this affects the initial integral. So we're going to replace x dx with 1/2 du. So let's write this as, let's write it like this. And ordinarily, I would just erase this and just modify it, but I really want to have a second line just so we can adequately compare the before and the after of this and see what the consequences might be. So we have 2 times the integral. We're going to replace, hang on, I want to color code it. I don't know about you guys, but I'm a visual learner. I like to use a lot of different colors to help me understand what's really happening in the problem. So x and dx are both blue. So we know that x times dx is equal to 1/2 du. So what that means is we can actually take all of this blue stuff and replace all of the blue with 1/2 du. So that's what I want to do in the next step of our integral problem. I'm going to replace x dx with 1/2 du. So I'm going to move it off to the side though. So instead of putting 1/2 on top like this and replacing x, I'm actually going to move it off to the side like that. And it has no effect on the problem. It's still going to be equivalent to the other way we had it before. So we're going to replace x dx with 1/2 du. And then du goes on top. And then the bottom, we're going to replace that with u because originally we set u equal to 1 plus x squared. So we have 1/2 du over u. Now this thing looks really, really familiar. But before we even get into that, we want to do the arithmetic part of this. We want to do some arithmetic simplification. So one of the most basic integral rules tells us that whenever we have a constant, it can be moved out front with no effect on the outcome of the value of this integral. So we can move it outside, things stay the same, and then something really nice happens. The 2 cancels with the 1/2. So we no longer have any number outside whatsoever. We just simply have the integral going from 0 to infinity of du divided by u. And we want to take the antiderivative of this. So the antiderivative would be natural log of u, and we would just continue from there. And because we're kind of running out of time, I don't really want to spend too much time on this problem. I just want to give you guys the basic groundwork and prerequisite knowledge and review needed to integrate something like this. The main goal is not to integrate, but to determine if we can integrate. I feel like that's much more important of a topic than the integration itself. We want to focus and emphasize on the conditions under which we actually can integrate something. We want to determine convergence absolutely before we can even determine if it can be integrated. Let's try another one. Let's try the integral going from 0 to 3 of 1 over square root of x. And we want to determine if the integral converges. So I know it doesn't look like it, but this actually follows the definition of the p-test we saw about maybe 10, 15 minutes ago. So let's rewrite this. Let's take our function, 1 over square root of x, but I'm going to rewrite it so that it is going to be a 1/2 power instead of a radical. So this would be p is equal to 1/2. And recall that whenever x is less than or equal to 1, it diverges. This definitely diverges. So that means we can't take the integral in the traditional sense, the way we're used to doing it. This converges, so we actually can't integrate this at all. Just a quick way to tell if we can actually integrate it before we spend a lot of time working on something that we can't integrate. So this diverges, so we can't integrate it. Let's try another one, shall we? Let's try 3, the integral going from -2 up to 3 of 1 over x to the 4th power dx. So this one is structured in a really similar way to the last one. This also follows that p-test pattern that we saw in the last problem. We can see that in this case, the exponent is 4, so p is 4. So recall that whenever p is greater than 1, it converges. Whenever p is less than or equal to 1, it diverges. So clearly we can see in this problem, p is equal to 4. So it definitely converges, definitely. So that's how we know we can actually integrate this. And this is a really simple integral. It's just going to be a basic power rule problem. So I don't really feel like it would be a really good use of our time to integrate this. If you want to do it on your own, by all means, go right ahead. But we're going to be moving on as far as this particular class lesson is concerned. So let's see what else there is. We've covered improper integrals. We've reviewed convergence and divergence, not only in a basic sense, but also in an integral sense. We have just reiterated that we can only integrate an improper integral if it converges to 0. It can't converge to anything but 0. And that is the main idea of the improper integral section. I feel like we're pretty solid on all that stuff, so we're going to be touching on something new starting right now. I want to talk about series and sequences. And then we'll use that as kind of a segue to get into the main goal, the main course, if you will, which happens to be infinite series. And we'll also be exploring convergence and divergence of infinite series. So let's talk about sequences and series just as a bit of a review. It is highly relevant to do so. So let's talk about what a sequence is, first of all. Give me a quick second. So a sequence is a list of numbers. It can be terminal, it can end, or it can be never ending. It can be infinite. A sequence could be something like this. Here, let me redo this real quick. Let's say we have 3/5 or 20/5 And then we have 5 over 125 as the third term in the sequence. And then we have 6 over 625. And then the fifth term is going to be 7 over 3,125. But we are going to be oscillating between positive and negative. And I'm sorry about the speed of this. We're going at the pace of a snail, and I apologize for that. I just don't have access to the tools that I normally use when I'm doing calculus on the go like this. So sorry about that. Doing the best I can with what's available. So we're going to be oscillating between positive and negative values. This is a fraction. They're all going to be fractions. So we start with a positive, and then we have a negative. And then another positive, and then another negative, and then another positive, and then we're going to continue. The 3 dots right here show that we're not going to stop right there. It's just going to keep continuing on and on forever. So is this a sequence or is it a series? This is a sequence. So a sequence is a list of numbers. A series is what we get when we add together numbers in a sequence. So you need a sequence in order to create a series. A series comes from a sequence. So let's see if we can create a rule that would give us a particular term on a particular value of n. So we're going to identify something called an index. So this is the first term, second term, third term, fourth term, fifth term. So this 1, 2, 3, 4, and 5, these numbers are indices. 1 is an index, 2 is an index. All of these numbers are particular indices. So we want to see if we can find a rule that would give us whatever occurs at a particular index. So that way we don't have to, if we wanted to find maybe the 10, that way we don't have to find 6, 7, 8, or 9. We can just jump all the way to 10. Having the rule for this particular sequence would help us find 10 more directly. And we can even find maybe 100 or even 1,000 without having to find all the numbers that come before it. So we are given the first 5 terms in the sequence. We can tell that the numerators start with 3 and increase by 1 whenever we go to the next term. The second term has a numerator of 4, and then the third term has a numerator of 5. In general, the nth term will have a numerator of n plus 2. So numerator is going to be n plus 2. So n is our index. These are values of n. 1, 2, 3, 4, and 5. These are all values of n. N just gives us a particular index. So if we want to find the numerator, all we need to do is take the index and add 2 to it. So this would be index of 1, 1 plus 2 is 3. Index is 2, 2 plus 2 is 4. Index right here is 3, 3 plus 2 is 5. So the numerator is always going to be the index plus 2, so n plus 2. And then we're going to divide that by, let's see what's really going on here. So we have 5, 25, 125. We're going to ignore the negatives for now. So we have 525, 125, 625, 3,125. We want to take a look. We want to just use our pattern recognition skills. We want to see if we can crack this code. So it's pretty easy to see that in order to get to the next term, we have to multiply it by 5. So 5 times 5 is 25. 25 times 5 is 125, and so on and so forth. But then how do we put that in terms of our index? How do we get n involved in that? So I think it's going to be 5 to some power. Let's see if 5 to the n power would work. So 5 to the first power is 5. 5 to the second power is 25. 5 to the third power is 125. So this works perfectly. We're just about finished. There's just one more thing we have to make sure we include in this. We have to include the fact that it oscillates back and forth between positives and negatives. We have to be clever and strategic in how we structure this so that we're able to make the first one positive, second negative, and then positive, and then negative, and then positive, and then negative, and then so on and so forth. It always just goes back and forth between positive and negative. We have to be strategic about how to word that algebraically. So we can see that whenever we have an odd index, we have an even term in the sequence. We can see that whenever we have an even index, we have a negative term in the sequence. So whenever the index is positive, it should be negative. Whenever the index is odd, it should be positive. So what that means is, well, in general, no matter what, these are, whenever we have anything that goes from positive to negative and then positive and negative, it's always going to be -1 to some power. And then what the power is what we have to figure out. We have to figure this out based on the pattern that occurs in this sequence. We start with we start with positive and then negative and then positive and then negative and then so on and so forth. So because we are starting with a positive, I think what we might want to do for this one would be the index -1. Because let's maybe start in the middle. Let's say that our index is 3. What is 3 minus 1? 3 minus 1 is 2. What is -1 to the second power? -1 to the second power, or actually -1 to any even power, is going to be just +1. So we need it to be n-1 to fit this pattern. So if we start with a positive number, it's always going to be n-1 as our power. But what if we started with negative? What if we had negative and then positive and then negative and then positive and so on and so forth? In that case, it would just be n. And this is one of those things you probably just want to memorize after a while. That whenever we start with the negative number, we have -1 to the n, -1 to the index. But then likewise, if we start with a positive, we want the power to be n-1. And then this is something that's going to be consistently true anytime we have something like this that oscillates between positive and negative. We just want to keep these rules in the bank and use them whenever they apply. So this is the completed rule we use to find any term in the sequence. So we could even use this to find a of 100. So let's say we wanted to do 1, 2, 3, maybe skip a whole bunch all the way down to 100. It's such a useful and powerful tool because now we don't have to find 6 and 7 and 8 and 9 and 10. We don't have to find 11, 12, blah, 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 97, 98, 99. We're able to skip all the way to 100 without doing the tedious busy work that we would normally have to do to get that high. So we just have to plug in 100 as our index. So this would be index of 100, n is 100, so that would be 100 plus 2, divided by 5 to the 100 power, which is a mind-bogglingly huge number. And then we have -1 to 100 minus 1. So 100 minus 1 is 99. 99 is an odd number. And recall that whenever we have an odd number, it's still going to be negative. So an odd exponent preserves the negativity. An even exponent makes it positive. So we have an odd result right here. That's 99, which means we're going to preserve the negativity, which means that the 100th term is going to be negative. It's going to be -102 divided by 5 to the 100th power. Like I said, it's a mind-bogglingly huge number. So we don't really care about what that value is. We're going to leave it like this. The main goal of this part of the class is to make sure we understand how to create an explicit formula to find a term in the sequence depending on an index that we choose. And we did that pretty well. We're able to have all these really useful tools at our disposal to help us quickly find the formula, find the pattern, crack the code. So that's a sequence. And I feel like that's basically all I wanted to cover as far as sequences are concerned. What I'd really like to do now is go over the concept of a series. So let's just give ourselves a basic definition of what a series is. So a series is what we get when we add together the terms of a sequence. And there is very, very special notation that we use for a series. You might have seen this symbol before. This is the capital Greek letter sigma. And whenever we see this symbol, it means we're taking the series. It means we're adding together a bunch of terms from a sequence. So a series is always going to have a starting point and an ending point, just like an integral. An integral always starts at the beginning and then always ends at this endpoint. A series is the exact same way, but we structure it a little bit differently. We have slightly different notation to tell us what we start with and what we end with. So the most common convention is to have a variable called I. I is the index. So we're going to start with an index, for example, of 0. It doesn't always have to be 0. You can start at whatever index you want. But for this particular example, I think we will just start with 0. Let's say we're going from 0 all the way up to, well, I want to do 4, but Later on, we're going to be doing things like this where we go all the way up to infinity. And we're going to be treating this in the same manner as we treat improper integrals. But I don't want to spoil the surprise. Let's just do a simple one. We're going to go up to 4. So let's say we have, here, let me come up with one real quick. Let's say we have -2, or actually, let's make it just 2, and then 4, and then 8, 16, 32, 64, 128, 256, and so on. This is our sequence. It's an infinite sequence, but not an infinite series. So the sequence never ends. It goes on and on forever. But the rules in our series right here tell us that we're strictly starting from 0 and going to 4. This will not be a never-ending series. The series will end, even if the sequence does not. So let's figure out how to evaluate this series. Oops, sorry, I meant to make this start with 1 instead. Integrals start with 0 a lot, but series typically start with 1 because this is the index. So that means we're going to plug in an index of 1. And if we plug in an index of 1, we get 2. And then we're going to add to it the thing we get when we plug in an index of 2, which is 4. Then we're going to plug in an index of 3, which is 8. And then we're going to plug in an index of 4. What do we get when we plug in an index of 4? We get 16. And we know we have to stop right there because we start at 1, we end at an index of 4. So we're actually going to stop right here. If we add everything together, we get 24 plus 6, which is 30. So the sum of this finite series is 30. This has, here, let's make it a bit more technical and structurally correct, syntactically correct. This would be A of n, and A of n is just the notation we use. It's the shorthand for a sequence. So this is telling us that we're adding the terms in a sequence starting with 1, ending at an index of 4. That is equal to 30. All right, so that's just a basic idea of how we evaluate a sequence, or evaluate the series, evaluate what we get when we start at a particular index and end at a particular index. This is how we assign a value to a series. So we don't really have enough time to cover the next thing I really wanted to cover today, so we'll have to do that in the next lesson. Next time, we're going to be covering convergence and divergence of series. We're going to be exploring series that actually, here, let me make that neater. In the next class, we're going to be exploring particular series that start at a finite endpoint but end with infinity. We're going to find that infinite series can converge and diverge in the same way that improper integrals can. So I'm going to be using improper integrals as kind of like a teaching tool to help us bridge the connection between calculus, between integrals and infinite series, to help us have a really solid understanding of the convergence of infinite series and the divergence of infinite series. So I hope that you found this helpful. Definitely let me know if you'd like a particular video made covering anything at all. I'm more than happy to make videos covering any particular topic, any particular problem you might want to go over, any solutions. So definitely just drop me an email if you'd like me to make a particular video just for you covering a particular topic. So that's it for today. Hope you have a wonderful evening. See you in the next video. Bye.